All right, everyone. Today we're going to tackle a topic that's absolutely fundamental to how the internet works, but let's be honest, can feel a little intimidating. The OSI model. So to make it easier to digest, we're going to break it down in a special interview format, layer by layer, to see how it all fits together. Let's dive in. So let me start with this. Have you ever just stopped and wondered what actually happens when you click on a link? I mean, how does that one simple action manage to grab information from a server that could be thousands of miles away, all in a fraction of a second? Well, the secret is a framework called the OSI model, which is basically the roadmap for all communication on the internet. Okay, a roadmap. I like that. So to understand this roadmap, let's start at the very top, the part that we all actually see and use every day. What exactly is the application layer? That's the perfect place to start. The application layer is pretty much what it sounds like. It's the layer where our apps, your web browser, your email client, even things like WhatsApp, actually connect to the network to send and receive information. It's the human-facing part of the whole system. And this layer is all around us. Seriously, every time you browse a website, you're using a protocol called HTTP or HTTPS. When you fire off an email, that's SMTP doing its thing. And DNS? DNS is the real magic. It's what turns a simple website name like google.com into the string of numbers, the IP address that the network actually understands. Got it. So our app has its data, but what about making sure everything's compatible? Computers all speak slightly different languages. So how does the network make sure a Mac can understand data coming from, say, a Windows server? What is the presentation layer? You've hit on its main job. The presentation layer is basically the network's universal translator. It has three critical tasks. First, it does that translation, converting all the data into a standard format that any application can understand. Second, and this is super important for security, it handles encryption, scrambling your sensitive information. And third, it often compresses the data to shrink it down, which means it can travel across the network much, much faster. And right below that, we have the session layer. Honestly, the best way to think of this layer is as the conversation manager. Its entire purpose is to open up a communication channel, keep that conversation going smoothly for as long as it needs to, and then, when it's all done, close it down cleanly. It manages the whole dialogue from start to finish. Okay, so the conversation is open. But now we get to the really crucial part, making sure the data actually gets from point A to point B reliably. How does the network guarantee that all the little pieces of a message show up and that they show up in the right order? This sounds like a job for the transport layer. That's exactly right. The best analogy for the transport layer is to think of it as the network's own dedicated delivery service. It takes these big chunks of data, breaks them into smaller, more manageable pieces we call segments, and then it takes full responsibility for getting them to their destination completely and correctly. Now, I've heard that this delivery service has two main ways of doing things, TCP and UDP. They're used for very different purposes, right? So what's the difference between them? Absolutely. Think of TCP, or Transmission Control Protocol, as registered mail. It's all about reliability. It establishes a firm connection, sends the data, and then waits for an acknowledgement receipt to confirm every single piece arrived safely. It's a bit slower, but it's guaranteed. On the flip side, you have UDP, the User Datagram Protocol. This is like standard mail. It's connectionless. It just sends the data out there and hopes for the best. It's way faster, but offers zero guarantees. Right, the postcard analogy is perfect. It really clarifies why you'd use UDP for things where speed is everything, like live video streaming or online gaming. If you miss a single frame in a video, it's much better to just skip it and keep the stream going, rather than halting everything just to get that one missed piece. It's all about being fast and efficient. Okay, so our data is packaged up and ready for delivery, but the internet is massive. How in the world does that little packet of data navigate the complex web to find the right destination? What is the job of the network layer? Well, if the transport layer is the local delivery service, then the network layer is like the entire global postal system. Its whole purpose is to look at the final destination, the IP address, and figure out the most efficient path for the data to take, letting it hop from router to router all across the globe. So, this layer is handling some really crucial tasks. First is logical addressing, which is just a fancy way of saying it gives every device a unique IP address. Second is routing. That's the process of choosing the best path. And third is the actual delivery of the packet across all those different networks that stand between you and the server. That makes perfect sense for global travel. But what about something much simpler? Like, how does data get from my computer to my printer when they're in the same room? Surely it doesn't need a global postal system for that? And you're absolutely right, it doesn't. That's where the data link layer steps in. This layer is all about local delivery. It uses a physical MAC address, which is a unique serial number literally burned into your device's hardware, to move data between devices that are on the exact same local network. And that brings us all the way down to the foundation of everything, the physical layer. At this point, we're not talking about logic or addresses anymore. This is the actual tangible stuff. We're talking Ethernet cables, fiber optics, the radio waves for your Wi-Fi. This is the layer that physically turns our digital ones and zeros into electrical pulses or signals of light and sends them across a wire. Okay, wow. We've just traced data's entire journey from an application on a screen all the way down to a pulse of light in a cable. But I have one last question to tie this all together. The IP address gets the data to the right computer, but how does the computer know which specific application, the browser or Spotify or email, is supposed to get that data? What is a port number? That's the perfect final piece of the puzzle. The best way to think about it is like this. An IP address is like the street address for a big apartment building. It gets the mail to the right building, your computer. The port number is the apartment number. It tells your computer exactly which apartment or which application the mail is for. And what's really cool is that there are standard, well-known port numbers for common things. For example, regular web traffic almost always goes to port 80, and secure web traffic goes to 443. This standardization is what lets your browser just connect to a website automatically without you having to figure anything out. And this is what brings it all home. When you combine all three, the IP address, the port number, and the protocol being used, like TCP, you get a complete, unique network connection. And that's called a socket. It's the full, specific address for any communication happening on the internet. It's an absolutely elegant and incredibly complex system, and it's working invisibly billions of times a second for all of us. So here's a final thought to leave you with. If the OSI model is this complex roadmap for our data, what part of this amazing invisible journey do you think is the most underappreciated? It's definitely something to think about the next time you click.